data that this matrix that we're actually sending to NASA is 10-bit words, and the analog data needs to be a 10-bit conversion. So, as you notice from this, the actual processor that we used is the 68HC16. Part of the advantage of that processor is it has a 16-bit analog to digital converter on board, so we can just take this in and convert it. The SPI also is sending out 10-bit words. That's also built in. We just put it into a buffer, and it will send it out at the right frequency, so we don't have to worry about keeping up timing-wise. The processor will do that for us automatically. The 4K FIFO, here, the reason we chose a 4K deep FIFO was because we were assured by the controller group that we wouldn't be seeing a burst of more than 4K at a time. So this should be enough for us to hold on to the data while we're sending it out. The analog mux that we chose was great because this is a 16-to-1 mux on one chip. We don't need multiple chips, and it also takes a 5-volt input. Some of the ones we looked at took plus 5 volt, minus 5 volt, which has been a little more difficult for the power team. The logic inside of here just looks at the control bus, decides when to actually clock this FIFO. One of the other advantages of this FIFO is that it's asynchronous, so we can put data into it and take it out completely independent. We don't have to worry about if they're writing it or anything like that. So the last thing we have in here is an exclusive OR, which actually just takes a clock from the SPI and the data from the SPI and Manchester encodes it. Just by putting the two in, we get a Manchester encoded data stream out, which is what the NASA transmitters are expecting to see. So this is pretty much the hardware. We have everything in. We figured out the right chips. We've ordered it. They're all arrived, and we should be putting it together within the next week. So go over the software on how everything's actually run now.